It's my pleasure to introduce Dr. Su-Chun Zhang, who is a professor in neuroscience and neurology here at the University of Wisconsin-Madison. He's also the Steenbach Professor in Behavioral and Neurosciences. And Dr. Zhang's lab has been the pioneer in the differentiation of human stem cells into different cell types of the nervous system, both to study development and also in disease modeling, and that's what he'll tell us about today.
Okay, thanks, Anita. I would like to thank Sanjay and the organizing committee for inviting me. A guy actually is not working on dementia or AD. But I have learned a lot from this symposium. But I will talk about something about age-related disorders because besides AD, there are many other neurodegenerative disorders, including Parkinson's, ALS, and so on and so forth, that are kind of age-related because they develop in 50s, 60s, and later. And this disease have the common issues. We don't know how they develop, and we have little option to deal with them. And it causes a huge burden to the person, to the family, and to the society. We don't know how to deal with this. I think it really goes back to some of the issues we have discussed throughout the summit. One is the model system. And this is the couple of slides I used for over a decade. I still want to use it because I feel that we use different kind of models, try to mimic what's going on in our human being. And of course, they have their relevance based on genetics, based on some of the anatomy, and based on some of the physiological aspects. And it's fast, and it's convenient, and so on and so forth. But there are also some other side of the model system, and we also discussed, including today, and that slide I used over a decade, and I actually highlighted a few red areas we just discussed this morning, and that was the same issue because we are dealing with age-related disorder, yet many of those animals, like mice, they do not age like us. And many of the models I listed, like Parkinson's disease, but as Eddie talked about in AD, it's the same, because we actually do not see neurodegeneration in these animals. And most of all, when we try to translate these findings from those models, and it's particularly difficult, at least in, for example, in ALS, amyotrophic lateral sclerosis, there are, I think, at least over 30 or 40 clinical trials for these drugs that have cured mice. Basically, zero works in patients except Loluzol, which extends the patient's life by 3 months or a few months, something like that. And so there are issues related to the model system. And so that means we may need some additional models or some complementary models. And I think Anita kind of touched in our breakup sessions. And so I'm going to talk about one model system that allows us to look at the human materials directly. That is the stem cell model. And those stem cells I'm talking about are mainly the pluripotent stem cells, which are either coming from embryonic, the early embryo, or we can reprogram them from adult tissue like blood or fibroblast skin cells. And this is easy to make, and and I actually made one by myself. I contribute a few drops of blood and made one, and everybody else should make one. And this cell, why they are useful? Because they actually can give rise to pretty much any kind of cells we talk about in our body, including neurons and glial cells or some other cells in the tissue. Now, will this stem cell be useful for modeling disease process? Probably not, equally difficult. And so there are many issues. So I list only a couple of issues. One, the cells coming from individual human being differ from each other greatly, way more than the animal models, because animal models are coming from inbred often, and so they are much more consistent. But in human being, when we generate the stem cell from each individual person, they differ from each other. And so when we try to model this kind of disease, it's extremely difficult. So that's the first barrier we have to overcome. The second one is the target cell we are going to look at. Let's say we want to, in AD, we want to look at cortical neurons or basal-forebrain cholinergic neurons. And we need to get the stem cell to those type of neurons. And the reality, on the other hand, is that we never got the cell to the homogeneous population in our culture petri dish. And perhaps another problem is that the cells that are differentiated from stem cells are usually very, very immature. They are equivalent to embryonic stage. Yet, the disease that develop in age-related degenerative disorders are in aged human being. Does it mean that it takes us 40, 50 years to get there? And so we have to come up with a way to get them first mature, or perhaps, as we discussed earlier, make them age fast in a petri dish so that we can look at them. And so I'm going to talk to you through using one animal, one disease model. It's called ALS. It's amyotrophic lateral sclerosis. It's a fatal disease, basically, when the patient, most of them, when the patient is diagnosed, they usually have 3 to 5 years to live. And I actually just got a call Monday when I came back from a patient. And this is mostly affecting motor neurons in the spinal cord and the cortex, and make the patient paralyzed and progress very quickly. The main pathology is that there's protein aggregation and then neuron degeneration. And we have quite a few transgenic lines from superoxide dismutase, TDP43 fuse, etc., for the past 2 decades. And it tells us quite a bit about how the neuron degenerate. But as I mentioned again, when it comes to therapeutics, it doesn't translate. And it happens similarly like AD. And so I'm going to tell you how we can use the stem cell model to look at some of the pathogenic process in AD, ALS, just as an example, but it should apply to other diseases, which we are working on. So the first question is, why, if there is a lot of variation, how can we deal with? So one thing we did was taking one type of a mutation, start with this familiar case. For example, it's a SOD mutation and specific mutation, like a D9A mutation. And we correct them using CRISPR, like Subject talked about, and so that they are on the same genetic background, but only with the point mutation. Alternatively, we actually introduce that particular mutation into the white, healthy background, and so we create another pair of mutations, so that we can look at side by side. Of course, you can increase the number, but that usually doesn't help too much. It helps to some degree. So that's how we overcome this variation between the human being. And then the second question is how to overcome the heterogeneity and immaturity. And that is something we are good at because we have been working on this for almost 2 decades. And so we can guide the cells very specific toward the motor neurons, very efficiently. We can get them to nearly 90% of the total population become motor neurons. And another part, which can be shown here, when we put into the chick embryo spinal cord, and they will go to the muscle and form connection with muscle. They do not go north, they only go south, wherever you put it. And so showing you that they are indeed motor neurons. Another part is that we make them mature fast. And so we actually use gamma secretase inhibitors so that they will kill all the, push all the progenitor cell to mature, and so that they can potentially display some of the disease-relevant phenotype. Okay, so now we got to overcome a few problems. Now, what kind of phenotypes are we going to look at? So initially, we just follow what has been done in the transgenic animals. The first thing is that we want to look at, because this is SOD mutation, whether there is increase of SOD and whether there is aggregation of SOD. And it turns out that in the patients derived cell, there is no increase in SOD. Not like in animals, there is several-fold increase. And whether it's at the messenger level or protein level. And in fact, that it's a decrease at the protein level. The red is a disease, and the black is controls. And so it's not increase. So why is, and we also look at under electron microscopy and look at whether there are aggregation of this protein, and we didn't see them. And so the patient cells, actually there is not such a huge increase. And when we look back, some of the pathology that was done from patient sample, and indeed it showed there is no clear increase in SOD1. But then when we look at back some of the old pathologies showing that there is indeed protein aggregation, but not SOD, instead there are some neurofilament. And then we look at our cells, cultured cells from patients. And you can see that in patient cells, you can see the swirling neurofilaments in the neurites and the cell body. And this is very much like what has been shown in patients, in ALS patient samples. And that shows that indeed we can actually see these phenotypes in cultured cells. So does this aggregation of neurofilament in this neuron will lead to some consequence? And so we follow the cells, look at over time, and it turns out that these neurons, these axons, form blebs, and you can also tell by this phosphorylate neurofilament protein showing that these axons are undergoing degeneration. And we can even use ELISA to measure how much this phosphorylate neurofilament is released to the medium, which actually is interesting because this phosphorylate neurofilament was used as a biomarker for ALS when you take cerebrospinal fluid and there is an increase in phosphorylate neurofilament. And we can actually see it in cultured neurons. And so when the axon undergo degeneration, and if we look at the further time, and this cell basically undergo this axon fragmented over time, and you can see this neuron dying because they show this caspase and turner positive cells. And so it's interesting because this is if we put them together and we take these neurons and play them within a week, we can begin to see neurofilament aggregation. And then later on, this exon degenerate and the cells pop out within just 3 weeks of time. We can kind of almost see the entire process that's happening in the ALS patients, which takes 50 to 60 years. But there is another part. When we see neurofilament aggregation in patient sample, we don't know when it happened. But in this case, it suggests that this aggregation actually happens early on, meaning that's the early event. So the question is, why? What happens? And so if there is protein aggregation, does it mean there is too much of this neurofilament going on there? And so we look at the level of neurofilament, the heavy chain, medium, and lower molecular weight chain, and compare with these controls or isogenic cells. And we didn't see increase. They are similar levels. Actually, in some cases, like the lower molecular weight, actually is decreased, at least at the message level. And at the protein level, it's the same. At the protein level, all the neurofilament decreased. But what decreased most is the neurofilament low molecular weight chain. So when we see protein aggregation, it doesn't mean there is too much. It can be too little. Why so? Because when we compare this proportion of different molecular weight neurofilament chains, and it turns out that the low molecular weight chain neurofilament is decreased more than any others. So that means the proportion of the neurofilament subunits is altered. Now remember that for the neurofilament to polymerize, form this filament structure, they need a stochastic proportion. If they cannot form in such a composition, they collapse. That's how we hypothesize they aggregate. And so that's very interesting because because this neurofilament proportion alters leads to aggregation. Now, we also mentioned, I kind of mentioned that the neurofilament aggregation is a relatively early event. So what if if the neurofilament proportion is altered, can we restore the neurofilament subunit proportion so that we can actually prevent the aggregation? And so we made an inducible system to induce the neurofilament low molecular weight chain to bring up the level to similar to the controls, and then look at whether the neurofilament aggregation and axonal degeneration can be prevented. And it turns out when we restore this, that the other neurofilament subunit can also be restored to a degree so that the proportion of these three subunits is close to normal. Then the protein aggregation is kind of reduced, and the axonal degeneration is reduced. So that means that the neurofilament dysregulation indeed is responsible in this case for the aggregation and the subsequent axonal degeneration. And so we did a bunch of other experiments, but because of time, I'm going to just summarize what we found using this system. And we found that this protein, the subunit downregulation is because of the degradation. And so if we correct the SOD mutation, we can actually restore this neurofilament subunit proportion, and so we can prevent the aggregation and the axonal degeneration. Because I mentioned that because the neurofilament dysregulation is responsible for the degenerative events, so what if we correct this part, even though the SOD mutation is still there? So when we correct only the neurofilament part without correcting the SOD, we still can correct the, prevent the degenerative process. So this set of experiments further confirms that the neurofilament misregulation or dysregulation is an early event in this degenerative process. And so that's why we actually begin to use this finding to look at whether we can capitalize it. And so we actually, like Su-Chun talked about, we CRISPR it by knocking in the luciferase into the neurofilament low molecular weight. And so that we can use patient cells to screen drugs that can restore the neurofilament level. And this is simply to show that this reporter line faithfully mimic what's happening in the patient cell. When we look at the luciferase level, and there is a reduction by 50%. And we are screening, we actually screened the FDA-approved drug library, and we have not found any single drug that actually can restore this. It's disappointing, but to a degree, it shows that why we couldn't find any drug that actually can treat ALS. And so we are now working with in cats in NIH to screen in bigger library. We can alternatively use another model. We also made a reporter, basically put a GFP into this neurofilament genes, and we can look at whether we can find something to prevent this aggregation of this neurofilament protein, which for both, we already made them to a high throughput screening platform, and so we are now working with NIH try to look at potential targets. So this is just an example to show you the stem cell model, how the stem cell can be used to model a disease process. We are working with a number of other diseases. And I'm going to use the remaining a few minutes to talk about another use of stem cell. Not so much for AD, but maybe useful for some other neurodegenerative disorders. Basically, I'm talking about whether the stem cell can be used as a cell therapy approach. I think Anita mentioned earlier that for that approach to work, we would like to have the disease that has relatively localized in anatomical region, and in particular focus on targeting only one or a limited number of cell types, and so that we can use the cell replacement approach. And I'm going to use Parkinson's disease as an example. Because Parkinson's disease is caused by degeneration of dopaminergic neuron in the substantial nigro, and so that they cannot talk to the basal ganglia neurons, and so that's why it leads to this motor function abnormality. Now, how are we going to deal with it? There are a number of issues we need to overcome. Because of time, I'm going to just go through a couple of issues. One, we have to get to the right type of cells, get to the right place, talk to the right target, and in a functional manner. And what if it when it goes wrong, and how are we going to deal with it? So for the cell types, I'm going to skip because we have done spend a lot of time, and we can generate this midbrain type of dopaminergic neuron. There are many different kinds of dopaminergic neuron, but you need the specific type of dopaminergic neuron. And they behave like a midbrain dopaminergic neuron. Now, the question is, how do you get the cells into the brain, and whether they actually behave like dopaminergic neuron in the brain, because once the cell get into the brain, you have no control. They will do follow their own way of doing things. And so I just want to give you one example. When we take the human cell and we transplant into the substantial nigro of a mouse, not human, and it turns out that these cells labeled with dark color, it's a human-specific marker, and we transplant to the nigro, and you can see these fibers goes well to the basal ganglia striatum. And that happens in the adult brain. And these cells actually do not go elsewhere. They only go there, go to the basal ganglia. Somehow they have eyes or whatever, they can see where to go. And that happens. And so that really gives some encouragement to the use of this stem cell-based clinical trial now going on in a number of institutions for Parkinson's disease. For me, I'm still concerned because even though the exon project there, the question is whether they do the right things, whether they talk to the right targets, and whether the communication is the correct one. And so we built a system try to address this type of question. And so we basically put a switch into the stem cells. And that switch is called DREAD, a designer receptor exclusively activated by designer drugs. And so we put two switches. One is active and one is inhibitory switch. And so we can turn on and off. And so that we can tell whether the cells are doing the right things. And so in vitro, when we differentiate the stem cell into dopaminergic neuron, and we can indeed switch on and off. So when we give a designer drug, say no, we can actually turn off the cell activity, action potential, and when we remove wash the drug away, and they will come back. And in contrast, the active form, we can stimulate the cell to work a lot harder. And so the cell at least work, the switch work in Petri dish. Now the question is whether they can do the job in vivo, in the brain. And so we transplant cell into the Parkinson's mouse brain, and you can see after 4 months, and the axon fill the entire striatum, and they do not go elsewhere. And they behave similarly whether they are the engineered cell or not. And so the question is whether they do the same thing. And so we actually took the brain slides and did the electrophysiology recording, and found that when we stimulate the cells by using the drug, and you can see the striatal cell, the GABA neurons will respond accordingly. And this response is dependent on the dopamine receptor, because when we use this receptor antagonist, we can block this effect. And so, so basically, how it works, the transplanted cells actually regulate the glutamate input to the striatal GABA neurons to regulate the motor function, and exactly works as what it has happened in the normal brain. And so that means it works really like they should be. And so then the question is whether you can regulate the behavior of the animals. And so we use a number of sets of behavior tests. I'm going to show you one, just the rotation test. When one side of the motor function is abnormal, and so usually the animal turns to one side, and this can be easily shown by looking at the rotation test. For example, after transplantation, usually the animal recovers, and so they will turn to both sides. When you let them do it, and you count them, and relatively equal on right or to the left. And then when we look at the animals transplanted with the cell with off switch, if we turn it off, that means the animal will go back to the one side turn. In this case, the left turn. Let's see, where is that? So when we look at this, and this animal will turn mostly to the left because we turn off the function of the transplanted cells. So meaning this animal, so we can actually control the activity of the neurons, transplanted neurons, and consequently we can control the behavior of the animal. And the same thing is for another animal. It already recovered, but this is an active form of switch, so we can push the hardest. That would mean they will turn to the right side further. And so that's what we expect them, and they will do so because we give this drug and they will just do a little bit more crazier. Because so in both cases, it shows that you can actually control the behavior of the transplanted cells and consequently the behavior of the animals. And so basically what I'm using just to show that the cells that are produced in a petri dish actually behave very much like those in the brain. And it suggests that they may be actually useful for therapeutics. So anyway, I use these two examples in this very brief discussion just to show that when we do not know all the details about pathogenesis, we can actually go with two relatively blunt approach. One is if we identify some lead, some phenotype, we can basically use this as a readout to screen whatever is available. And an alternative, when the cells are gone in many neurodegenerative disorders, what can we do? And maybe a simple way is to replace them. Of course, I'm too simplistic, but just for discussion. And it was done by my previous postdocs. Most of them are left, and Hong is a clinician scientist. She's now in her hospital working on the ALS project. And another two postdocs, Yu-Jun and Man, did the Parkinson's project. They have their own labs in Chinese Academy of Science. And he is an electrophysiologist. He's leaving next month. I'm looking for an electrophysiologist if you are interested. And because I have another job in Singapore, if anybody is interested in a faculty job, tenure check, full salary, great startup, and so on and so forth. Thank you.